Hello folks, in this video we're going to introduce the concepts of inertia, velocity, and acceleration. We're going to talk about motion. So we'll start with our story about the inertial dampener that we introduced earlier. In this situation, what do we mean by inertial dampener and why is that necessary? So here we see a simple depiction of, in the Star Trek universe, the Starship Enterprise moving to warp speed corresponding to speeds at the speed of light and faster. So what is it about this process that requires an inertial dampener? Well, to talk about that, we first need to think about the concept of inertia and exactly what that means. So what is inertia? We can see another example of it here in this situation where, and you've seen this, I'm sure you've seen this, where somebody takes tablecloth and yanks it really hard. You'll notice that there's the action in the wrist that yanks it down. But nonetheless, the plates and the glasses, etc., remain on the table. So why is that? All right, why is that? Well, it's due to this process of inertia. So exactly what is this thing called inertia? Well, it's very simply resistance to changes in motion. That's it. If you think about this in this particular GIF, we've got this situation where the plates remain on the table because they are resisting changes in motion. And this is a whole key concept to the Newtonian concept of motion and inertia. And it relates to what we call Newton's first law, which basically says an object in motion tends to stay in motion at constant speed. An object at rest tends to stay at rest. In order to change the motion, for example, in order to change the speed, or in order to push an object from rest into motion, forces are required. So in the absence of forces, there's a tendency for an object to remain doing whatever it's doing, moving in a straight line at a constant speed or remaining at rest. A force is required to change that. So that resistance to change is referred to as inertia, in that the degree of inertia determines the force necessary to change the motion. And that's actually fairly important. And that gets into Newton's second law. You might imagine if there's a first law, there's got to be a second law, there's got to be a third law. Maybe you've heard of those. And we'll be getting to those, but in this video, we're just going to concentrate on some of the basic concepts of the first law. All right, so how do we know this? I mean, what's this business about motion? We're talking about these concepts, and all concepts like this, all laws require some sort of experimental measurements. So what are the measurements that we need to make here? We talk about motion. Well, this should be pretty obvious. This is not a hard thing. You've certainly done that. How do you know that something's moving? All right, well, you know that it changes its position with time, right? If you see an object changing its position with time, and of course that's what your perspective is on time. That's a whole another issue philosophically and in terms of physics that we won't get into here. But if an object changes its position, if there's an observation, if there's a measurement that shows a change in position with time, then we've got motion. Now we know that there are various properties of objects, and we've talked about mass of those objects, and how does that affect inertia? As you might expect, you know this from experience. This is intuitive that a more massive object requires more force to move it. So mass does relate to this inertia. A heavier object, something that has more mass, is going to require more force, and therefore it's going to have greater inertia. We'll get into those concepts as well, but we're going to focus in this video on motion with respect to time. So when we talk about motion with respect to time, we talk about speed, right? And the speed represents a rate of change in position. When we make a measurement and we measure the rate of change, we're actually measuring it over a finite distance and over a finite period of time. And we can calculate the speed based on that. The speed is equal to distance divided by time. That's simple enough, right? That's speed, right? So for example, units of speed, distance meters per second, for example, would be units of speed. Or we could talk miles per hour, which is something that most of you are probably most familiar with. If you're driving a car, you're wanting to know how many miles per hour that you're driving. That's speed, and again, it's distance divided by time. This is a simple measure of speed. All right, so let's look at an example here, and this is an example that we're going to talk about briefly in this video, but in a subsequent video, we're going to work through a problem associated with this. So here we've got a situation of, unfortunately, a Yankee pitcher. I'm a big baseball fan, and I really don't like the Yankees, but nonetheless, I've got this pitcher throwing a baseball and the batter hitting it. So when we talk about this, pitcher's mound, we're going to ask the question about what's the reaction time for a batter. The batter has to make a decision about when to swing the bat, where to swing the bat, and so how much time does a batter have to make that decision? Pitcher's mound and what's called the rubber of the pitcher's mound is 60 feet 6 inches away. And so if I pause this, I'm going to let it go here so we can see this a little bit better. All right, that little white strip there that you barely see is 60 feet 6 inches away from home plate. All right, so if a pitcher's thrown a fastball, a good fastball these days might be 95 miles per hour. There are some pitchers that are in the upper 90s to 100 miles per hour. And if you know anything about baseball, you know that pitchers really work hard to fool batters, and that means mixing up the speeds, throwing at different speeds, putting spin on the ball that causes it to curve in different directions, all to fool the batter, because the batter doesn't have a lot of time to make a decision to react. And that's what we're asking at this point. If we've got the pitcher's mound 60 feet 6 inches away and it's 95 miles per hour, how much time does it take for the ball to arrive at home plate? Now, this, of course, is an approximation. When we talk about 95 miles per hour, that is actually an average speed. The ball is not moving at a constant speed. If you were to actually measure it over shorter periods of time during its trajectory, you'd find that it's actually moving fastest at the point of release from the pitcher, and it actually slows down due to air resistance and such before it reaches home plate. So we're going to say this 95 miles per hour is the average speed over that distance. The other thing is, of course, that the reality is, if you can see from that little short video, that when the pitcher releases the ball is actually much closer at the point of release to home plate than 60 feet 6 inches. So as you can see, back here is the rubber, and when he's releasing the ball, he's quite a distance in front of that rubber at the point of release. So that again is the calculation we would do here to calculate how much time it takes for the ball to reach home plate. In reality, the batter is going to have even less time than that because the point of release is closer than 60 feet 6 inches. So we're going to ask how much time does it take for the ball to reach home plate? And so you can think about this. Again, I'm setting the problem up here. We're going to talk about it in a future video just to run through this particular calculation. But that would be an example of how we're going to be doing calculations associated with speed. All right. The other thing is the term velocity is actually fairly important, and you might actually have used velocity and speed interchangeably at some point, but they are not the same. Speed represents a magnitude, a distance traveled per time, again, like meters per second. Velocity deals with both speed and direction. So a little bit of misspelling here. So it's speed and direction, right? And so what that means is that it's what we call a vector quantity because it has a direction associated with it. And this little diagram here kind of shows that arrow represents the direction of motion. The arrow is what's called a vector, and the length of that vector represents the magnitude of the motion. So for example, you can say this is 60 kilometers per hour moving east in this direction. Here's one this is 30 kilometers per hour. Here's one that's 60 kilometers per hour moving in the same direction. You notice the length of that arrow, that vector, is greater because the speed is greater. And here's one that shows 60 kilometers per hour. It is the same length as this vector, but it's moving in a different direction. So the arrow represents that. And you might say, well, why do we care? It does turn out that when we start talking about properties of systems and where velocity is important, directions are actually fairly critical. We look at forces that are acting on different things, the direction of the vector and the velocity is fairly important. So velocity, while speed only has a positive value, you can only have positive speeds, you can have negative velocities, and that would indicate a direction. So for example, in this little diagram, the direction moving, when it says east here, but moving from left to right, we could say that's a positive direction. And so the velocity would be plus 30 kilometers per hour. If it was moving from right to left, if the arrow was pointing to the left and was 30 kilometers per hour was the speed, the velocity would be negative 30 kilometers per hour. So that's actually fairly important, and we'll be coming back to that in future videos and future discussions. All right, so when we talk about things like acceleration, velocity change, we're talking about something called acceleration. So velocity represents the rate of change of position. Acceleration represents the rate of change in velocity. So when something's accelerating, for example, if you're in the car, all right, and you're in a stationary position when you hit the gas pedal, or if you're an electric car, hit the pedal that causes the car to move faster, you're accelerating, right? You've used that term, you know what it means, but that is a change in velocity. You're starting at rest, so that's zero velocity, all right? As you accelerate, say you're accelerating up to 60 miles per hour, the velocity and the speed is changing throughout that period where you're going from 0 to 60 kilometers per hour. So the rate at which it changes corresponds to acceleration. If you're going from 0 to 60 miles per hour in 5 seconds, that's a much greater rate of change and a much greater acceleration than if you went from 0 to 60 in 10 seconds, right? So acceleration represents that rate of change. And that was speed. It can also represent a direction change. So, for example, if you are in the car and you're turning left, then your direction is changing, and that change in direction also corresponds to acceleration. So acceleration is important to note, corresponds to both the speed change and a direction change because we're talking about the velocity, a change in velocity. And again, that is important with regard to important physical quantities and interactions, understanding that acceleration means both speed change and direction change. All right. So obviously, if the speed is increasing, the acceleration again can have a sign like velocity. If the speed increases, if the velocity increases, it has a positive sign. If it decreases, and of course the term we use for that would be deceleration, but deceleration would have a negative sign if the velocity is decreasing during a particular process. All right, and so here this represents some examples of those changes when we talk about, again, the car going from 30 to 60 kilometers per hour, and that would be a positive acceleration. This would be a negative acceleration going from 60 to 30 kilometers per hour. And of course, we also talked about change in direction as well, corresponding to acceleration in the strict sense. All right, so another problem that we're going to be working on in a future video is this, going back to this question of impulse power and warp power in the Star Trek universe. So in the Star Trek universe, warp speed corresponds to speeds faster than the speed of light. Impulse is less than that, but it's also, impulse power in the Star Trek universe is also pretty fast. For example, maximum impulse power in the Star Trek universe might be about half the speed of light, which again, speed of light is 186,282 miles per second, right, in our system, or roughly 2.998 times 10 to the 8th meters per second. So it's pretty darn fast. And so impulse power at half the speed of light is also pretty fast. So what we're going to be doing is working on a calculation here to calculate the acceleration if the Enterprise is moving from 0 to 0.5 speed of light in a period of 5 seconds. And what is that acceleration? What would that acceleration be? Clearly, that's a whole lot more than moving from 0 to 60 miles per hour in 5 seconds. This is an incredible bit of acceleration. And when we do that calculation, what we're going to do is actually probably heard the term g-forces used when referring to, for example, fighter jets and pilots of fighter jets having to experience serious g-forces, or propelling astronauts and rockets to space have to be able to experience serious g-forces. What the heck does that mean? That's related to acceleration. We'll talk about that in a future video. But that issue of moving and accelerating at such high rates is why the Enterprise needs inertial dampeners. All right. If you think about sitting in a chair or sitting in the seat of your car, and the car accelerates from 0 to 60 miles per hour, you know you get pressed back against that seat from that acceleration. All right. Think about going from 0 to 0.5 times the speed of light. You're getting pushed back in that seat because of inertia. All right. Inertia says that your body wants to stay in motion at constant speed or at rest until forces are applied. You get pushed back against that seat when its acceleration occurs because of inertia. All right. If you're going from 0 to 0.5 times the speed of light, that's a serious acceleration, and the inertial forces associated with that would kill you. So these fictional inertial dampeners that are on the Enterprise actually compensate for that. How? It's fiction, right? How do they compensate for that? It's fiction, but they're in there to compensate for that effect so that the folks who are on the starship aren't killed by that sudden acceleration. But we'll talk about this in future videos. We'll be working on the problem to actually show how all this works. So stay tuned. We're going to have some fun.